All right, let's go ahead and get started here. So, I did not send out a poll about the recitation. We're just gonna do Wednesdays. It just works better for. It was split with the votes, and then it just works better with the TAs and the rooms and stuff for Wednesday. So it's gonna be what the syllabus says. Wednesdays at 4 o'clock, I think, is when the recitation's gonna be. I'll have him record them, and so we can post them afterwards if for some reason you want to go there and you can't make it to it. I think that's the only thing in terms of announcements. Did anybody ride that Big Sky Biggie this weekend? Nobody? All right. It was just a mountain bike race. I did it. It was 30 miles, and I came in 186th. So, literally, no joke, 2 hours after when my son finished. So, and I was beaten by, no joke, a woman in her 70s. She passed me. Her and I were battling quite a while, but then at some point she pulled away and I never saw her again. So, and I looked, she beat me by about 30 minutes too, but I finished. The whole point of that is I am still recovering. I am still recovering from this. So there's 34 miles, 5,000 feet of vertical up at Big Sky with a ton of mud. So if you are a mountain biker, you should consider doing it next year. It's right at the beginning when school starts. It's pretty fun, but also a terrible experience at the same time. All right, so I'll try to pull it together here. As I get older, it's harder to recover. Okay, so what we did last time, we just kind of introduced and defined position. We defined velocity, right, in general terms. We talked about frame of reference. We did so in, the book does it, and then we showed you what ChatGPT came out and did it in Gen Z slang. I went, in my other class, I teach pre-stressed concrete. We went even further, and I started having it write it as other people. I had this little introduction to pre-stressed concrete. I had ChatGPT write it like Abraham Lincoln would, and it was pretty funny. That was a pretty good one. My absolute favorite was writing it how Donald Trump would write it, right, or would say it, which is not political. He does have a very recognizable speech pattern, and it used a term in there somewhere that pre-stressed concrete was going to make concrete great again, and I thought that was pretty good. And you don't give it any prompts. You just say, can you write it like this? You could have it write it like Obama. You could have it write it like all sorts of people, and ChatGPT will do it, and it comes out pretty good. Okay. Anyways, so then now what we're going to do is we're going to start out with 1D motion. And we're going to talk about the different types of problems you will see in terms of acceleration down here. And then the importance of doing stuff in 1D motion is it's very simple. We're going to learn the basics. And then what we learn in 1D stuff, we're going to apply to 2D stuff. Because 2D and 3D problems in this particle stuff is just multiple 1D problems. So once we learn one 1D problem, then we can apply it to the 2D and 3D problems pretty easily. Okay, so this is the same thing that the book does that you guys don't have yet, but I'm going to give out some chapters here. But I am going to assign a homework today that's going to be due on Friday. It's going to be pretty short because it is such a short amount of time that I'm giving you, but it'll just kind of get you started, and I'll give you the problem statements and everything you need for that to go from there. Okay, so we start out 1D stuff. The book starts out with this as well. What's nice about 1D is there's no vectors yet. We haven't introduced vectors into this deal yet. Come on. My iPad's been having issues. There we go. No vectors. And then we'll just say what I just said there. 2D and 3D problems. Ooh, whoa. Problems are just multiple 1D problems. Bless you. Okay. No vectors, 2D and 3D problems. That's why we start with it. That's why the book starts with this. It starts very simple. A lot of this stuff is just going to be absolute straight up review for you, at least starting out. Right? So the book starts out, we define position when we're talking about 1D stuff. That position vector, we're just going to call S. Kind of weird, but that's just what they do. For all the S's in the word position. Right? So we're going to drop the vector. See, I don't put a line over that S, just meaning that, look, this is just, now it's just a scalar. Right? Maybe that's why they use S, because it's a scalar now. There's no direction associated with it. Okay, velocity. Velocity is just going to be the integral of ds dt, right? The rate change of position. We can call that s dot. Again, no vectors, right? If there's position, if we had a plot of what position is doing, some random line over here, velocity is going to be the slope of that position. Right? Again, I'll review. Velocity and 1. That's sometimes how you write slopes. Right? It goes up v and over 1. So just showing that's what the slope is. Acceleration in these 1D problems, acceleration is just going to be dv dt, which we can then just call v dot. We can also call that s double dot. Second derivative of the position. And again, if we did a plot, some random plot over on the side of what velocity is, then acceleration would be the slope of that line. Acceleration and 1. So some general stuff for 1D. All right, this is where things get a little more interesting. Types of problems, right? So I said before in this class, we're going to lay out procedures on how to solve problems. This is one of those. This is the first time we're going to see a procedure, right? They always say not to be a cookbook engineer, where you're like, oh, I don't know how to do this, and then you look up you look up the way to solve it. However, in this class, I absolutely do it, right? We're going to lay it out. We're going to lay out these processes. You're going to open up a problem. You're going to look to see what type of problem it is. You're going to look over here and see if it fits one of these things. And each one of these things, we're going to go over the solution method for each one of these, okay? So we could have acceleration a function of time. We could have acceleration that is constant, right? And those two are kind of related to each other. Acceleration a function of velocity, or acceleration a function of position. So now what we're going to do is go through each one of these and talk about how you solve them. Acceleration a function of time and constant acceleration, that's review. Acceleration a function of velocity and acceleration a function of position, that should be new. Okay. All right. Acceleration a function of time. What are some examples of something moving where the acceleration would be a function of time? Or I think the force changing with time. Yeah.
0 to 60 on a...
Absolutely. Yep. In a car. If you're in a car and you step on the gas, right, do you instantly get up to the right acceleration? No, right? And you think, right, forces and accelerations are related to each other. So when you step on the gas, right, you feel a little bit of pressure on your back, and then you feel more pressure on your back, and then more pressure on your back as it's accelerating, right? And so a car engine, right, has to start out lower RPMs and then gets higher RPMs, and you get the force changes, right? That's acceleration of function time. Absolutely, changes with time, right? I did have the opportunity in Hawaii this last summer to drive a Tesla. That was fantastic, right? In that case, it is instant acceleration. You step on the pedal, right, and then it's just like, you get instantly all of your, but no sound, right? I misled you there, right? You just step on the accelerator and it just goes. It's pretty cool. Anybody ridden in a Tesla before? They're pretty fantastic. Turns out you could just test drive them. Who knew, right? We were walking through downtown Honolulu and they had a Tesla shop, and we're like, hey. We just went in there, and then like I was daring my kids to touch them, right? And we're just like, and then I got one of them to sit in one of them, and I was like, oh God. And then they came over and were like, we're on our way out. Sorry, I apologize. And they're like, no, you guys want to test drive one? It's like, are you sure, right? And then they're like, oh yeah, go for it. Your insurance for your other car is gonna cover it. And I was like, I don't know. So I called my insurance, like, are you sure you're going to cover this shit? And they did. And so then we took it out, and it was phenomenal. It was really cool. I mean, like the windshield just like started down here and then went up all the way over our heads, and the doors open. It was a very expensive one. It was like $200,000 to let me drive around on. Didn't have a wheel, didn't have a steering wheel. It had a yoke, is that what you call it? A yoke? Didn't like it. I wasn't a fan. Right? I like to drive with my arm up like this. I couldn't. I had to have a... It's pretty cool though, because they even had, a little distracted here, but they even had like, I get in it and there's these little teeny mirrors. I was like, well, this is dangerous. Like, I'm not gonna be able to see all the cars around me. Then you get inside and you look at the main screen and it has like an overview of your car and like an image of all the cars around you at all times, right? And then like, yeah, then you could even just say, like, literally you could say, drive for me, and then you have to hold the steering wheel still, but the car will actually drive for you and like move around and work you around. I wasn't ready for it. It was pretty cool though. Okay, so acceleration is a function of time. Cars, absolutely. That's the easiest one to think of there. Okay. All right, give you an example. A car. Right? Anything where the force changes with time. You can see right there, you can see why I type so much, right? There's me trying to write in my handwriting here. Force changes with time. Okay. All right, so how do we solve these problems? Right, we're gonna do this quite a bit. So acceleration, we start out, so we're gonna go to velocity. We're gonna define velocity first, and then we're gonna define position. But usually start out with an acceleration equation, right? Acceleration a function of time. That's usually an equation. So in a problem, we're going to do some examples right after this, but acceleration is going to be a function of time. So that's going to be an equation that's given to you, okay? And we know that that's equal to dv dt, right? We just defined that, the rate change of velocity, right? And then how you solve these problems is what I do. What I think to myself is like, oh, I need to get all the t's next to each other, okay? So what I do is I bring that dt and I put it on the left-hand side because there's a t over there, acceleration function of time. So then what we get right here is we get a of t dt is equal to dv. Okay? So I just moved that dt from the right-hand side to the left-hand side. We're going to do this a lot throughout the next couple weeks. Okay? And then at this point, I want to get rid of the dt's, right? And so I got to integrate to do that, right? And so I throw an integral on here, integral, and you got to integrate both sides when you do that. So I integrate both sides. And this is, you should recognize this, right? To solve a problem, one of these problems, we integrate the acceleration equation to get the velocity, right? And that's if acceleration is the derivative of the position, you integrate to kind of go the other direction. But this is just kind of mathematically how you would do it, okay? At this point, I always make these, this is kind of a shortcut to do this, but I always make this go from T naught to T, and I make this go from V naught to V. Technically, you're not allowed to do that. I cannot make my definite integrals be the same variable as my variable down below. Like this should be a dummy variable. You might remember that if you're back in your calculus classes. I shouldn't make that a t and a dt. I should make that another variable because this is a dt. Just math says you can't do it, but I do it anyway because I'm a rebel, okay? And so I'll do that. That's just kind of a shorthand way of doing this. Okay, so at this point, you would carry out those integrals, right? The integral on the left-hand side, I can't carry out that integral right now because I don't know what a of t is, right? So we're going to leave that in integral form. But this side, the right-hand side, I can. This just becomes v minus v naught. The right-hand side does, right? It's just 1 times dv is one way to think of that, right? And so if you carry out that, it's just v minus v naught, right? And then what we're after... I mean, the way I think about this is I'm after what v is right here, this v right here. I want velocity as a function of time. I want velocity equation. So I'm after that v right there. I'm after the same v. So at this point, what you do is you just solve for v. You just do algebra and solve for v. And if you do that, that gives you this. Right? So if I want velocity as a function of time, if I'm given acceleration as a function of time, I just take the initial velocity, v naught, and I add on to it the integral of a of t dt from t naught to t. And again, a of t would be something that was given to you. It would be a function that was given to you. And so that's how you would go that direction. Okay? All right. Let me just box this guy off. That was one of the key equations. All right, one more step. Let's take, now that I know velocity is a function of time, can I get position as a function of time? So we do the same idea here. We say velocity is equal to ds dt. Right? And in this case, velocity, I should write that with let me add in a function of t here. Velocity function of time. So again, I do the same thing. I want all the t's together, so I move that dt to the left-hand side, and I leave the ds out there. V of t dt is equal to ds. Right? Then I integrate both sides like I did last time. And this is going from t naught to t. This is going from s naught to s. We can evaluate the right-hand side. That's just going to be s minus s naught. Rearrange that equation, solve it, and this time solving for this s right here. Just rearrange the equation, solving for that s, and I get this. Okay. So if you're working through problems and you open up your homework and you're like, oh, look at this, my acceleration is a function of time. Then I would open up this sucker and say, well, how do I solve acceleration as a function of time? Well, I just integrate with respect to time, and then I add on the initial velocity, and it gives me velocity as a function of time. Once I have velocity as a function of time, I then come down here and I integrate that, and then I can pull out the position. So that should be review, right? At least in some capacity, you should remember a little bit of that. If you guys remember a little bit of that, right? Okay, so that's not too bad. Maybe not, maybe you haven't seen it in this form before, but that's where that comes from. Okay, so now let's come down. That's acceleration of function of time, right? One very much related to that is constant acceleration. The reason I say it's related to it is the same as acceleration of function of time. It's just a constant as a function of time. It doesn't change with time, and so it's just. So we actually use both of these methods right here. We use both of these methods right here. It's just now in that case, this is a constant and this is a constant. And so you just carry out these integrals with that being a constant. You can actually evaluate it further. Before we get there though, let me just say this. All of these types of problems, at least for the first couple weeks, are one of two forms. Either they give you, here's a problem, here is the equation for acceleration as a function of time, and they give that to you. So they start out with acceleration. It's a very common thing to know, right? Like you know your acceleration of your vehicle, and you know you can measure forces and things like that. We know acceleration function of time. So you're given acceleration of function of time, and then it starts asking you questions about velocity and position. And so when it does that, you come in here and say, oh, here's velocity function of time. This is how you move that direction. You start out with acceleration and how you move through position. The other way that they do it is they flip it and they give you information about the position, and then they ask you about velocity and acceleration. That's actually a little bit easier of a problem because now you're taking derivatives as opposed to integrals. But they're one of two ways. You're either going to start out with acceleration, right, and move this way, right, or you start out with position and you move this direction, right. And it's a little easier when you start out with position and move to velocity because you just take derivatives of things, right. It's not as interesting, but just keep that in mind. They're all kind of focused like that. Okay, what's an example of constant acceleration? Something with a constant acceleration. Gravity, yeah, kind of, right? I mean, in our world, and what we're going to do in this class, for the most part, we're going to say gravity is constant, and so a lot of our problems, absolutely, that's what we're going to use in our main thing. Is gravity constant? No. Right? It's not. It is. I mean, if you believe in these sort of things, but if you go far, it's related to the distance between the two objects, right? Like we're all on the Earth and we all feel the same gravity, but if we start moving away from Earth, the pull of gravity on you is less, right? Your mass affects your gravity, so does the distance between the two things, right? And so if you're doing orbital mechanics, right? Absolutely, gravity is not constant. You need to take that into consideration. In our world right now, for most of our problems, we're going to say that gravity is indeed constant. Okay, so we're going to say gravity, kind of, right? In this class, we were doing 9.8 meters per second squared or 32.2 in feet per second squared. No tens. I always get a student using a 10 for the gravity. That's left over from some high school physics, I think. Okay, so to solve these, right? Acceleration, this is just going to be a naught, right? And that's going to be equal to dv dt, right? So again, just the same method we just laid out before. A naught dt goes on that side is equal to dv. Integrate both sides. T naught to t, v naught to v. Right? You can actually carry out that whole integral at this point, right? Because a naught is the equation. So you can integrate that from t naught to t and v naught to v. What's this? A naught times t minus t naught is equal to v minus v naught. Right? And then you just solve for this v. Again, you're after this v. And when you solve it, right, you solve everything for v. This is what you get. Pretty easy, right? You just put the v naught on the other side, and this is what you get. This, too, should be review, right? In your physics class, you might have started out with taking the integral of something, but then you're like, oh, I'm going to deal with gravity. I'm going to say that's constant. And then you can simplify the equation down to this. And so that might have been like what you wrote on your equation sheet for your physics class. Right? What is velocity given that acceleration, constant acceleration? Okay, you do the same thing here for accelerations, or sorry, for positions. V of t is equal to ds dt. The dt goes on the other side. V of t dt is equal to ds. Integrate this from t naught to t, and this from s naught to s. And then what you take this is the equation that goes right there. Okay. So you put that whole equation in for that v of t. You integrate that with respect to time from t naught to t. And when you do that, you get this. That 2 should be very familiar to you. Okay. A naught times t minus t naught squared over 2 plus v naught times t minus t naught plus s naught. Oftentimes in physics, they just assume time starts at 0, and so a naught times t squared over 2, right? You remember that. You guys use that, correct? Maybe you remember? You do remember? Good. No remember? No remembering? You've purged that information? It takes a while in college before you learn that, like, something you learned in another class, you're actually using it. Like, you shouldn't purge it every time. Certain classes you could purge, right? Certain classes you could purge, but these mechanics courses, don't purge them, okay? Study just enough to get it. Okay, sometimes you may want velocity as a function of position, given a constant acceleration. We're going to introduce a little technique here. Sometimes it might happen, actually, and you'll see that in some of your homework problems that you might want this. So, A naught is equal to dv dt, okay? We're gonna do a little trick here. Remember, you can multiply anything by 1, right? And so we're gonna multiply this by ds over ds, right? ds over ds, that's just 1, right? So we're gonna multiply that right-hand side by ds over ds. We're gonna move the ds. I'm gonna flip the ds and the dt, which you could do because it's just multiplication, so it doesn't matter which order you do them in. So we're just gonna flip this and make this dv ds. Clean that up a little bit, hold on. dv ds times ds dt. Okay, I just spread that ds out a little bit, okay? What's ds over dt? It's velocity, right? How position changes with respect to time. So that right there is velocity. And so this is becomes dv ds times v. This is actually a use of the chain rule. We're gonna do this a couple more times, even today, where we use this chain rule. But we could do that. Mathematically, that all makes sense. We didn't break any rules there. But that's called the chain rule. So we come down here, and we got dv ds times v is equal to a naught. Right, just kind of simplified what we had written up above there. In this case, I'm going to put all the v's together and all the non-v's. So this is going to become v dv is equal to a naught ds. I'm going to integrate this from v naught to v, integrate this from s naught to s. And we could do that, right, because a naught is just a constant, but we're integrating it with respect to s naught t, right? And if you carry out that integral on both sides, then you get this. All right, we kind of skipped the actual integral, but I figure you can do that. That, too, might be an equation that you recognize. Right? If I wanted velocity as a function of position, this is it. Right? And this equation only works for constant acceleration. Okay? So it's another side note here. Like, you might be seeing all these integrals, and you're like, oh my God, this sucks. We only do integrals for like the first couple weeks, and then we never touch an integral the rest of the semester, okay? I don't like it. In fact, I think sometimes the problems the first couple weeks, I think, are a little bit harder than some of the later on stuff, because these ones are a little bit, like I said, you got some integrals and some calculus and some little feeling around of like, what kind of problem is this? How, what's the best solution method? All the other ones later on in the semester, we're solving more complex problems, the procedure is more straightforward. So just hang with me. You might be going, oh my God, I hate dynamics already. Don't give up on it yet. You can see that when I first put together these skeleton notes, I wasn't too good at guessing how much space I needed, so I apologize for wasted paper. We'll get that. It gets better as we go along. Okay, let's get into one that's a little bit more exciting here. The other thing I was going to mention too, I forgot to mention this, is calculators. I'm gonna say this a lot. Absolutely, if you've got a calculator that does integrals and stuff, please use them, okay? If you have a calculator that has a solver on it, please use it. I'm a huge proponent. My favorite calculator is the TI-89. It's beautiful. It's got the pretty print. Who's all got an 89? Oh, that's it. What are you guys rocking? What are you guys rocking? Oh, you poor sons of bitches. I swear to you, listen to me here. So far in your career, right, your math class takes away your calculator, right? And you have to solve these problems without a calculator. All of your engineering classes from here on out, you can use whatever calculator you want, right? They don't care, right? It is so worth the money getting a TI-89 or what's the other one, an Inspire? Has anybody got an Inspire? Yeah, it's something that has a little bit more power behind it. Those 84s are gross, okay? That's what you use in high school, correct? That's what you had it from high school, and you're like, oh, I keep using this. There are some tools that are built into like the 89 and the inspiration stuff. Like, it is so worth it, right? Ask for it for Christmas, right? Ask for it for your birthday. Your parents will be excited to give you a calculator. If you ask for that, they would be so excited, right? I'm serious. Skip the bars one weekend, save that money, and get yourself a TI-89. I'll show you. I'll bring in my TI-89 sometime. I'll tell you this. I've had a lot of students come back to me over the years, and and offer praise. It's never about me. It's for my advice to get them the 89. That's all it is. They come back. It's like, hey man, thank you so much for that 89. It really helped me through the rest of my career. Okay, do it. Anybody, you guys love your 89s? Those that you have it, it's so much better than those 84s, right? Absolutely. And we'll see, when I get into some problems, I literally will get to a point where there's like a big equation. I was like, shit, I'm not gonna do this by hand. And I just say, calculator, boop, 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 and then out pops the answer. And then it always is right too, versus you guys tried to do it by hand. Do it, get the 89. I also should mention I own stock in TI, and no, I don't. Full disclosure. No, I should be. I should, though, how much I try to sell these things. The only thing that should really make you angry when you're paying, I don't know, what does the 89 cost? Like $200, $150, $100?
Like 130.
130, right? The only thing that you should have a major issue with is that when I went through college, I had a TI-89 and it was exactly the same fucking thing, right? That should make you think of what your phones have done. Like when I went through college, they didn't have cell phones. Well, we did. We had little flip phones. We had the big car phones. Anyways, it was a big deal. Yet your calculator is exactly the same. And I mean, what a moneymaker these calculators have been for TI, right? Because they want to give you power, but they don't want to give you too much power. So then they hold you at that 89 and you never get any more. Like why there isn't a TI-89 app for your phone, I don't know. I don't know why. Because it could do all that. Anyways. If you're tired of listening to me talk about calculators right now, just wait. I'm gonna do it all. I'm gonna do it all freaking semester. Okay, let's get it back to this. Acceleration a function of velocity. What's an example of acceleration being a function of velocity? Drag. Exactly. Right. When the faster something moves through a viscous fluid, the more pressure that's back. Right. So. When a skydiver jumps out, right, he has initial pressure on him as he jumps out of there, and then that pressure increases as the velocity goes out. The wind hits him faster. Or in a car, and you're going a certain speed, you have the wind resistance versus going faster, you have more wind resistance, right? Absolutely. Acceleration function velocity, drag is the best example, right? Or viscous flow, or like anything flowing through a viscous medium, right? So let's write that, drag. Right. Those things are going to be functions of velocity. This might be new. I'm not sure if you guys covered this in physics or not, right? So to solve these problems, they're a little bit different, right? Because you start out with acceleration of function of velocity. This part doesn't change though, right? It's still dv dt. Right? Acceleration function of velocity. But what we did last time is I put that dt over with the acceleration equation. This is many of you are going to do this. Okay? You're going to say, all right, I get to this stage right here. I want to solve this problem. I'm just going to integrate with respect to time. Put that dt over there, and I'm going to integrate with respect to time. You can't do that, right? Because acceleration is not a function of time. Acceleration in this case is a function of velocity. So you have to be careful. And so you get the wrong answer in the book. I don't understand why I get the wrong answer. Look back and make sure you chose the right method to solve these things. Right? And so what we do is, like I said, I always think to myself is I put all the T's together and the V's together, right? So in this case, I can do that, right? It gets a little weird because I'm going to take this dt and I'm going to put it over here. I'm going to take that AV and I'm going to put it on the bottom over there. But you can do that, right? So that's what we're going to do. That's how you solve these problems, right? So I move the dt to the left-hand side. dt, right, is equal to dv over acceleration of function of velocity. Right? Again, that is something that's going to be given to you in the problem statement. You're going to have an equation for that, and it's going to have a v in it. Okay? That's how you solve that. So on this side, right, or I guess you can rewrite that a little bit cleaner. You could say that this is going to be 1 over, so the inverse of this equation, 1 over av dv. Right? I integrate this from v naught to v, and I integrate this from t naught to t. Okay, and that's about as broken down as we can get this. Okay, what we're after velocity. Once you're given the acceleration, we're after velocity as a function of time in this case, and so what we're after is this v. Okay. You're after that v. So what you do is you carry out the integrals, the one on the left, that's just going to be t minus t naught, and then on the right-hand side, you're going to have a big equation with a v in it, right? And then what you do, once you get that v, you solve for that v. You just do algebra and rearrange everything and get everything in terms of v on one side, okay? And so that's about all you can do. That's about as broken down as we can get it. And we'll do an example either today or on Wednesday, kind of demonstrate this. So I usually just write a note, carry out and solve for variable v. Which gives you v of t. I say, when we do an example, you'll see it play out. But you solve for that v, and so you have v on one side and a function of t's on the other side. And so you're going to isolate that v. And that v, with all the t's on the other side, that's v of t. And then once you get v of t, then you're mostly there. Right, so just be careful of that. When you have acceleration of function of velocity, no, you can't just integrate with respect to time. You can't do that because it's not a function of time. It's a function of position, so you have to carry it out like that. Oh, I have to close my... Okay. So that's how you get velocity. Right, now to get position, that one's pretty straightforward. When you're done with the one above it, you get velocity as a function of time. And so you just go velocity of function of time is equal to ds dt. That one's straightforward, right? Because now we just do v of t dt is equal to ds. We integrate t naught to t, s naught to s. Right, and then that, you're after that s. This is going to give you s as a function of time. That's the same thing we did before with the constant acceleration and acceleration of function of time. It's the same method to go to position from them because you have velocity as a function of time. Okay. Sometimes, just one more little sometimes. We'll do this. Just like we did before, we say if we're after the function of v of s, sometimes you want that. There's a shortcut. There's a couple different ways you could do this. Again, we'll do some examples, but there's a shortcut using the chain rule. If your acceleration a function of position of velocity, and we want to skip right to velocity as a function of position instead of velocity function of time. The one we just showed up above, we gave you velocity function of time, but you can actually go velocity as a function of position here using the chain rule. So we start out with just the definition of acceleration. And we do this again, this little chain rule trick where this is dv, ds, ds. Oh, hold on. I made a mistake. This should be a t right there. It should be dvt, dvdt, not a dvds. Right here. That guy. I had an s there, should be t. S is coming here when we multiply it by ds over ds. Same trick we did before. That's just the velocity. So then this becomes dv ds times the velocity. And so I put all the v's together and everything that's not s. So you can see that there's, on the right-hand side, we have dvv, and we have a of v. So all those we're going to put together, and then that ds we're going to isolate as well. And so we're just going to rearrange those equations as such. And so this becomes ds v over a of v dv. Let me integrate both sides. S naught s, v naught v. And then afterwards you solve for that v and you get v of s. After that v. What I mean by after that v, if you remember back to how you take integrals, right? You take the integral, right? And then you plug in this guy and then you subtract out this guy. And when you do that, when you put this in as a variable, right, then it'd just be a big algebraic equation. And then with the v with a v floating around. And you take that v, and that's what you solve for, right? What I do to get that is I plug it into my TI-89, boop, 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 and then I say solve, and it goes boop, out pops the whole thing, right? You could even put it in the form of an integral on one side and an integral on the other side, and then set them equal to each other and say solve for v, and it'll do it. Absolutely acceptable in this class. I promote it. Do it. In fact, if you could get away without showing me the work, it'd be great. It'd be wonderful. Okay, last one. Okay. Box this little key finding here. Okay. Acceleration function of position. What's an acceleration function of position? Examples. What's that? Magnets. Absolutely. Great. Yeah. The closer two magnets are to each other, the more attraction they have. The further they are away from each other, the less attraction they have. Right? And so that's what I mean by acceleration of function of position. It's all related to forces, right? And so think about the forces. Like you take two magnets, they get them close to each other, and the forces are getting really big, right? And then the further they get away, there isn't a lot of force, right? And so those are tied to acceleration. So magnets, absolutely. What's another one? Oh, yeah? Magnets?
Gravity.
Real gravity. Yep. Real gravity. We just talked about that, right? Fake gravity, or what we're going to use in this class, it's okay to use constant gravity, but real gravity, the further you get away from each other, the less attraction there is. One more. One more pretty straightforward one. Springs. Springs, absolutely, right? The more you compress a spring, the more it pushes back, the bigger the force is. The bigger the force, the more acceleration there's going to be. So springs, for sure. Okay. So if you see a spring type problem, again, so these types of problems, again, what you're going to do is you're usually going to start out with an equation for acceleration. So instead of, acceleration will be some function of position, right? It'll be given to you, and then you have to move either to velocity and then to position, or you start out with position and move your way back to velocity and then acceleration. Okay, so in these cases, we start out with acceleration of function of position, a of s. That's equal to dv dt. Right? You always start out with that main definition, right? It's always the time rate of change of the position, right? But again, what I gotta do is I'm supposed to isolate, I'm gonna try to put all the variables that are similar to each other next to each other, right? And so in this case, it's a little complicated, right? I can't move the stuff around to isolate v's, because now I got a v, a t, and an s. And so I gotta do something special here. And so what we do is we use that chain rule again to kind of get rid of one of those variables, right? And so we'll use the chain rule again. This is gonna be dv ds. Oh. ds dt. ds dt again is position. Is velocity. So now we get a of s is equal to dv ds times v. Now I could do it, right? Now I only have two variables floating around, v's and s's. So now I put all the s's together and all the v's together. I get a of s ds is equal to v dv. I integrate this from s naught to s, and I integrate this from v naught to v. Right? And so again, like we did before, you carry out those integrals, right? You can't really carry out the integrals yet because I don't know what some of those equations are yet. You'd be given this equation. I can't simplify it more than this, because you'd be given a of s and you're gonna have to do that integral, right? And again, what you're after is that v right there. So you kind of put everything in there and you solve for that v, and so you get, afterwards, you're gonna get v as a function of position. Before we got velocity, on the previous one, we got velocity as a function of time, but this time we're gonna get velocity as a function of position. So we have to go one more, we have to it's not as straightforward to go to position now because that's a function of velocity function position, not time. Okay, so we come down to position. One last little step we have to do here. We get velocity of function of position is equal to ds dt. Okay, I got to rearrange this thing, put all the s's together and all the t's together. Not too bad here. So I put the dt on the left and bring the v of s to the right. dt is equal to 1 over velocity function of position ds. And then integrate this. Integrate this from t naught to t. Integrate this from v naught to v. Sorry, s naught to s, sorry. And then we carry that out. We're after this s right here. You solve for that s. And this becomes s as a function of time is what you get out of it. Okay. So did you guys, in physics, did you do acceleration of function of time, or say acceleration of function of velocity and acceleration of function of position? Or is that new? Is that new? We'll say it's new. You have a lot of blank faces here. What do you remember from that class? I liked the original physics. Okay. So then I'll give you some examples of what we're gonna do. So what we're gonna do, first thing on Wednesday, we're just gonna dive in, right? Missiles launched 100 Gs for 3 seconds, then a rocket undergoes -4 Gs deceleration. How long does it take to reach 15 kilometers, right? So you're starting out with acceleration of constant acceleration, right? And they give us that equation for the constant acceleration. And then we work our way to velocity, and then we work our way to position. So that'd be an example of that. Then we'll do this example, right? Mass released from rest, spring is unstretched, right? Oh, this is messed up a little bit. I want to move some stuff around. But anyways, they start out and it gives us the acceleration of function of position, and it asks us for what is the max velocity, and then what's the max position that it gets to. And then here's another one. This is an acceleration of function of time, followed by an acceleration of function of velocity, right? And so we'll solve this. And it's all just 1D motion. It doesn't talk about different distances and stuff. So we're gonna do one type of each of the problems that we just went through. That's right. And then we're gonna get into 2D motion, 2D and 3D motion after that. Talk about different coordinate systems with that. So that's where we're headed. Again, you'll see an assignment today, and then Wednesday we'll do some examples, and I think the recitation will do even more examples, and then we have a homework due on Friday, and you're on your way. It's a shorter homework just because we won't have covered a lot, and it's kind of short week. So, all right, break. Yeah.
Do you know if the books in the library have
I don't know. I don't think.